Okay, now I would like to explain about the Newman's formula and energy density in a magnetic field. So first one, Newman's formula. So by using this formula we can find the mutual inductance between two irregular closed loops. So consider two closed loops C1 and C2. Here C1 and C2, two closed loops, any random shape as shown in figure. So both the closed loops are stationary loops. These two are stationary loops placed in a linear medium. For linear medium, the mutual inductance between first circuit to second circuit and second circuit to first circuit is same. Okay, let I1 and I2 be the currents flowing through the closed loop C1 and C2. C1 current equals to I1 and C2 current equals to I2. So let R be the distance of separation between C1 and C2. Here R is the distance vector from DL1 to DL2. So and let S1 and S2 be the surfaces of loop 1 and loop 2 respectively. So C1 surface area equals to S1, C2 surface area equals to S2. So first here two loops C1 and C2, so irregular closed loops. Next I1 is C1 current, I2 is C2 current, and the distance between DL1 and DL2 is R. So point P located at DL2. So we know that the vector magnetic potential at point P due to loop 1 is given by A1 equals to mu by 4 pi closed line integral I1 dl1 bar by R, or it equals to mu I1 by 4 pi. So closed line integral dl1 by R. So already we derived this expression vector magnetic potential, and we know that the relation between vector magnetic potential and magnetic flux density B1 bar equals to del bar cross A1 bar. So next one, let the pi 1 to be the flux linking coil 2 due to current in coil 1. So this is coil 1 flux and it links with the circuit 2 or coil 2, and the flux linkages lambda 1 2 or psi 1 2 equals to number of turns into magnetic flux. So assume here number of turns equals to 1. First coil number of turns equals to 1. So second circuit number of turns equals to 1. So the flux linkages equals to pi 1 2, it equals to surface integral B1 bar dot ds2 bar. So assume the circuits of singleton. That means first coil and second coil number of turns equals to 1. And it is a linear medium. So M12 equals to M12 equals to M21 equals to M. Okay, this is M12 equals to M21 equals to M. So then the lambda 12 equals to pi 12, it equals to surface integral B1 bar dot ds2 bar. Okay, next the flux linkages. Flux linkages equals to, okay, here number of turns equals to 1. So flux linkages lambda 12 equals to 1 into pi 12. Number of turns into flux equals to flux linkages. Here number of turns equals to 1. So flux linkages equals to flux. So it equals to surface integral del bar cross A bar dot ds2 bar. Okay, so pi 12 equals to surface integral B1 bar dot ds2 bar, but B1 bar equals to del bar cross A1 bar. So by substituting B1 bar, so next equation, so pi 12 equals to surface integral del bar cross A bar dot ds2 bar. So next by applying Stokes theorem, so convert the surface integration into line integration. So after by applying Stokes theorem we can write the surface integral del bar cross A1 bar dot ds2 bar equals to closed line integral A1 bar dot dl2 bar. So next lambda 12 equals to closed line integral A1 bar dot dl2 bar. Okay, A1 bar equals to equation mu I1 by 4 pi closed line integral C1 dl1 by R. Okay, by substituting A1 bar we get lambda 12 equals to, so first one, so closed line integral, okay, C2 closed line integral. Next this is A1 bar expression into dl2 bar, or lambda 12 equals to mu I1 by 4 pi closed line integral C2 closed line integral C1 dl1 bar into dl2 bar by R. The mutual inductance equals to flux linkages by current. So M12 equals to flux linkages by current. Here current equals to I1. So lambda 12 by, okay, this is lambda 12 by I1 equals to M12. It equals to expression mu by 4 pi closed line integral C2 closed line integral C1 dl1 bar dot dl2 by R. So inductance units are henries. So similarly, the mutual inductance between second coil to first coil M21 equals to mu by 4 pi C1 integration C2 integration dl1 bar dot dl2 by r henries. So by using these formulas, we can find the mutual inductance between two coils or two circuits. Okay, next one, the energy stored and energy density. Okay, this is inductor. The voltage applied across the inductor equals to V and current flowing through the inductor equals to I. So generally, in order to establish a magnetic field around a coil, energy is required. In inductor, in order to establish a magnetic field, energy is required, but no energy is needed to maintain this energy. It means the energy is stored in the form of magnetic field. Inductor stores the electrical energy in the form of magnetic field. If the current supplied to the inductor increases from 0 to I, here the supplied voltage is sinusoidal voltage. If the current supplied to the inductor increases from 0 to I and voltage applied to the inductor is V, then the source supplying power equal to the V into I. Okay, we know that power equals to formula voltage into current. Here inductor current equals to I and voltage equals to V. So finally the power supplied to the inductor equals to V into I. Okay, the energy stored in dt time is VI into dt. Energy equals to power into time. Okay, in dt time, the energy stored by the inductor equals to VI into dt. If we neglect the resistance of the inductor, the supplied energy stored in inductor. So assume this is ideal inductor. So internal resistance equals to 0. The total supplied energy to the inductor is equals to storing energy or energy stored by the inductor. In dt time, the energy equals to differential energy. It is represented by dW. It equals to VI into dt. Okay, we know that the voltage across the inductor V equals to L into di by dt. So dW equals to VI into dt and V equals to L into di by dt. L into di by dt, I into dt. So dt cancel. dW equals to L into I di. Total energy W equals to integral dW. It equals to integral L into I di. So L constant value, integral I into di equals to I square by 2. So finally the energy stored by the inductor W equals to 1 by 2 Li square. Energy units are joules. Okay, next one, the energy density. The energy stored by the inductor per unit volume. Per unit volume is called energy density. So energy density mathematical representation, energy stored by the inductor divided by volume of the inductor. Okay, we know that the energy stored by the inductor equals to 1 by 2 Li square and inductor volume equals to inductor area into inductor length, A into L. So L equals to formula flux linkages by current. Flux linkages equals to N into pi divided by I. So substitute L equals to N pi by I. E equals to 1 by 2 N pi by I into I square by A into L. So it equals to 1 by 2 Ni by L into pi by A. Or E equals to 1 by 2 into H into B. Or E bar equals to 1 by 2 B bar dot H bar. So energy density represented by E bar and units are joules per meter cube. Okay, we know that B bar equals to mu into H bar. So by substituting B bar equals to mu into H bar, we get the energy density equals to 1 by 2 mu H square. If we substitute H bar equals to B by mu, H bar equals to B by mu, we get this expression E bar equals to or E equals to 1 by 2 B square by mu joules per meter cube. The energy density is a scalar quantity. It is not E bar, just E. It is a scalar quantity. So E equals to 1 by 2 B bar dot H bar or E equals to 1 by 2 mu into H square or E equals to 1 by 2 B square by mu. The energy density, different formulas. Finally, so by using Newman's formula, so we can find the mutual inductance between two closed loops, okay, which are random in shape. So next to the energy stored by the inductor formula 1 by 2 Li square and energy density of the inductor or the energy density in a magnetic field equals to 1 by 2 B bar dot H bar or it equals to 1 by 2 mu into H square or it equals to 1 by 2 B square by mu. Energy density units are joules per meter cube. Energy units are joules. and mutual inductance units are henries.